Welcome to solverfy.
Okay, in this problem we have single slit interference by a beam of electrons. We know the slit width for the single slit, we know the distance from the slit to the screen, and we know that the first minimum occurs at 20 degrees from the central axis. We're asked to find the velocity of these incoming electrons, and we're asked to find the angle to the second minimum in this interference pattern where no electrons should be appearing. So the equations are rather simple. We only need the single slit interference equation and the definition of a de Broglie wavelength. For constants, we only need h bar, or rather h, the Planck constant. So let's jump into it. So to start, we can use the interference pattern, the interference equation. A sine theta is n lambda. For the first interference, we set n equal to 1. And we can rearrange. Actually, we don't even need to rearrange. We can find lambda because we know a and theta. Plugging those numbers in, we end up with a lambda equal to 1.026 times 10 to the negative 7. So fairly long wavelength electrons. With that done, we can simply use the definition of a de Broglie wavelength, h over p. Assuming that these aren't relativistic, we can use the simple expression for momentum, mv, and we can rearrange to isolate the velocity v. Comes out to be h over n lambda. So when we plug in numbers, we have a result of 7,096 meters per second. So these electrons are pretty fast. Now for part B, we're asked to find the theta to the second minimum. So we can once again use the single slit interference equation, except now n is equal to 2. So we have 2 lambda instead of simply lambda. Now that we know what lambda is, we can simply isolate theta. This will be our theta 2, which comes out to be an arc sine of 2 lambda over a. Plugging in numbers, we have about 43 degrees. So these are the main results. All we needed to use was a definition of a wavelength for a particle with mass and the single slit interference equation. That's it. Thank you very much.